I will begin with a word of prayer here. So, let me start. Dear Father, we thank you for this day. Again, I thank you for the students in this class. And just ask you just guide our steps today. Help me to not make mistakes. At least if I make a mistake, help it to be hilarious. And I just pray that you'd be glorified at what we do, Lord. In your name I pray, Lord Jesus. Amen. All right. So it occurs to me that I can't quite go on to set theory yet because I have neglected to talk about a couple things in the material before set theory. And so let's just wrap that up, and then we'll transition to so-called naive set theory in the last portion of this class, all right? So just a couple of preliminary examples. Some of these are really easy. Example 1, here's the claim: if f of n equals 2 to the n, then there exists n in the natural numbers such that f of n is prime. This is going to be a very short proof. All right, this is a very, very short proof, this one, because the proof goes like this. N equals to 1 is a natural number, and f of 1 equals 2 to the 1 equals to 2 is prime. Thus, there exists n in n such that, f of n 2 to the n is prime. There you go. Not much to say there, right? Another example, similarly easy. Let's see here. Suppose we have m and b in the reals such that m is not equal to 0. All right? The claim is this: there exists a unique x-intercept to the line y equals to mx plus b. Right? Again, the proof here is not really that complicated. It goes like this. So proof, suppose, let m and b be real numbers with m not equals to 0 if x, let's say x naught in the reals is an x-intercept of y equals mx plus b, then what do we have? And I shouldn't say is an x-intercept, I should say, this is where the ambiguity comes into play a little bit. Do we want to say an x-intercept is referred to by the x-coordinate or as the point of interception, right? And people will go both ways, all right? So let me just, the point of interception. In other words, should the answer here be like, if you're asking for an intercept, should it just be the x value you're talking about, or should it always be what? It's kind of boring. It's always x comma 0, right? If it's an x-intercept. So, let's call the x point of intersection x naught y naught has what? Y naught equals to, mx naught plus b, but it's also equal to 0, right? That's what we mean by x-intercept. Thus, what? What's x naught equal to? We have mx naught is equal to minus b, hence x naught is equal to minus b over m. Since m is not equal to 0, we can divide, right? So how would we prove this is unique? a lot of times I would just say, we're done. It's clear it's unique because m and b are given, right, numbers, and the ratio of two given numbers is a single number, right? But if you like, if your reader's not convinced, you can do this maneuver here. You can say, okay, so suppose x1 is another, that was supposed to be another x-intercept of y equals mx plus b, right? Then x1 is equal to minus b over m, but that's equal to x naught, right? So therefore, x1 is equal to x naught. Hence, there exists a unique x-intercept to y equals to mx plus b, where, you know, x is equal to minus b over m as it happens. So completing the thought with what I wrote in red is usually what's expected in like a proof course. If I'm in like a calculus course or something, I don't feel the need to write what I wrote in red because, you know, it's pretty evident from writing a formula that it's unique. But formulas can be deceiving, and it's a good practice to check for uniqueness. All right, so that's that. So I already talked about these things a little bit before, but I thought it would be healthy for us to have another pair of examples. So there they are. This next example, it introduces you to a trick that maybe you haven't seen before. And also this example is just a little bit, I like this example. It gives a little bit more breadth here. So all functions on R are the sum of an even and an odd function. So one of my hidden goals in this class, by the way, guys, is to review math that you might be rusty on. And this is possibly one of those things. Maybe not, but all right, so let me write this symbolically. So like we're saying is, for all, functions, for all f, let's see here, such that, so we have f as a function on R to R, right? Sorry, I have a mental block here. Let me erase that. I don't like what I wrote. Where's my eraser? Hiding. All right, like what did I do? Oh, I had the good sense to define the set of all functions before I got into this. I said let script f be set of all functions on R. All right. So what that means is that the function has a domain of all real numbers, and its codomain is also real numbers. So its range has to be a subset of real numbers. All right. So here's another way to look at the claim that I just wrote symbolically, which I think is helpful for us. So like for all f in script f, so that's for all functions, there exists f naught and f1 in f. All right, and what's the condition on all this? Such that f is equal to f sub 0 plus f sub e. All right, and brackets here, for all x in R, f sub 0 of minus x is equal to f minus, rather, O is for odd, minus f sub 0 of x. All right. Okay. I guess there's different ways you could package this. This is how I did it when I wrote the notes. I'll stick with it. And for all x in R, probably could have combined these two here, you know. F sub e of minus x is equal to f sub e of x. So technically speaking, this is not entirely, I mean, I wouldn't have to write this symbolic sentence down just for the sake of doing the proof here. I'm just doing it as another exercise in writing symbolic logic, okay? All right. So anyway, my claim is that this is true, all right? So here's the proof. So this is a for all claim, right? So I have to take f in the set of all functions, right? Hence, f is a function from the reals to the reals, right? Period. Then, here's the trick. Observe f of x, I should say for x in the reals. All right? F of x is equal to 1/2 f of x minus f of minus x plus 1/2 f of x plus f of minus x. Notice that this makes sense because why? As my little brother used to say when he was very little, 'cause be why. I'm like, why don't you say refrigerator? Why do you say frigilator? And he'd be like, 'cause be why. But he was cute, so he got away with it. Anyway, so so this makes sense because x and minus x are both in the domain because the domain's all real numbers, right? So it's symmetric about the origin, the domain is. So we can, and what am I doing? Like what's going on here? This and this, when you put these together, what you got? See? It's just 0, right? So we've added 0 there, and we've also used that 1 is 1/2 plus 1/2. So this is an identity, all right? So let this, let this define f sub o of x. Let this piece right here define f sub e of x. You can check f sub 0 of minus x is equal to minus f sub 0 of x, and f sub e of minus x is equal to f sub e of x. Thus, the claim follows. Now this thing I just did with you can check, you can try that on a test, right? It depends on how much of the proof that is, whether or not you can get away with that. I can get away with that in here because I have other things to cover, and I already have, well, you can't take points away from me. Well, can you? I don't know, I guess you can. But anyway, my point is, it's obvious. Don't make me write it down, please. But you can check this, right? So admittedly, there's a gap in my proof because I haven't shown you those details, right? Fine. The larger point here is if we're asked to do a for all proof, we have to give evidence that the claim holds for an arbitrary element of the set. Here, the set happens to be a set of functions. Have you guys ever seen this before? Yes, no, maybe so. Well, if you've read the notes, maybe you've seen it. I don't know if you guys are doing that or not, but you should. An example of this that's near and dear to my heart is to, apply it to the exponential function, right? If we do this for the exponential function, if we look at e to the x is equal to 1/2 e to the x minus e to the minus x plus 1/2 e to the x plus e to the minus x. What this is a decomposition of the exponential function into an even and an odd function. But these have names, right? The odd part of the exponential is the hyperbolic sine. This is sinh. The even part of the exponential is the hyperbolic cosine, also known as cosh. So, all right, well, there's that. Fun fact, this is very interesting, a fun digression. is if you look at e to the I theta equals to cosine theta plus I sine theta, then if you plug in minus theta, what cosine is an even function, right? So cosine of minus theta is just what? Cosine of theta, right? So cosine, so if I plug in minus theta, I get cosine theta, but the sine is odd, right? So I pull the minus out from sine, so I get minus I sine theta. If you look at these two equations right here, you can add and subtract them, right? Take these, if you allow me this short Mingus style calculation here. This will give me, after adding and subtracting and doing some division, that cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta is 1/2I e to the I theta minus e to the minus I theta. And so this is intriguing, and just one of the many similarities between hyperbolic sine, cosine, and regular sine and cosine. There's a very interesting interplay between these two worlds. And in fact, you can use the formulas. Did I miss my 2i?
Oh, no, something else.
Oh, go for it.
Is f of x equals 0, is that even and odd?
So the constant function 0?
Yeah.
Yes, that function is both even and odd.
Okay.
And it's also equal to it's also equal to 1/2 of itself minus itself plus 1/2 of itself minus plus itself. But yes, you're right. The only function which is both even and odd is in fact the 0 function. That's a very good observation. In linear algebra, that becomes the observation that f can be written as the direct sum decomposition of the set of all even functions and the set of all even odd functions. Like any function can be written uniquely as the sum of an even and an odd function, and the only function which is intersecting, the only function which is both categories, is actually the 0 function. So that observation is critical to writing this, but this is not for this course. This is a Math 321 comment, so we'll leave it for there. But it's his fault. What's your name?
Nolan.
Nolan. It's all Nolan's fault. All right, so let me go on here. So finally, let's see here. Oh man, where'd it go? Trying to find my words. Necessary versus sufficient. We should talk about that for a second here. So what's necessary, if I can spell, necessary versus sufficient. I can't spell with it. Conditions. So a necessary condition is one which is needed for the condition to follow. A sufficient, on the other hand, a condition which is sufficient, it's said to be sufficient when the conclusion follows automatically from the basis of that condition alone. All right? So necessary is needed, sufficient guarantees. All right? But, well, it's best to show you some examples here. So let's see here, example 4. So my examples are mostly from Calculus 2. If we consider the series, the sum, all right, n equals 0 to infinity of c sub n, right? The condition, limit as n goes to infinity of c sub n equals to 0 is a blank condition. However, this limit as n goes to infinity of c sub n equals to 0 is not a blank condition, since the sum and I said 0 here. If you guys don't mind, I'd like to make this a 1 just for the sake of not cluttering this example. However, the sum n equals 1 to infinity, since the sum of n equals 1 to infinity of 1 over n diverges, yet has c sub n equals to 1 over n goes to 0 as n goes to infinity. So you guys fill in the blanks for me. What do I need to put there? So this top thing we called the what? This is the nth term test, right? If you have a convergent series, it must satisfy the nth term test. It's necessary. It's a necessary condition, right? However, it's not sufficient to guarantee convergence, right? It's not a sufficient condition because, why? Because we have this example, right? The harmonic series diverges despite the fact that it has terms which go to 0. This is responsible for 30% of the points lost in that part of Calculus 2, not understanding this sentence. This is easily, it's just, it can't be fixed. We've tried. Every professor's tried. No one can fix this. Get the students to understand this. We've tried. My professor, I got a PhD, my PhD advisor, taught students for 50 years. He's a way better professor than I'll ever be. But he told me, he's like, if more than 20% of Calculus 2 understands convergence and divergence, you've done a very good job. This is a man who's taught calculus for like 50 years. And he's not a dummy. It's just very hard to fully understand. Anyway, but that's my example. Another example of a, I'll open the floor. Can you guys tell me another example of a sufficient condition for a series to converge in Calculus 2? How about this? What if I'm looking at s equals to, like 1 minus a half plus a third minus a fourth plus ... What's this equal to? Anybody know?
From 0 to infinity, 1 over n plus 1.
So you're giving me, I'll start you at 1. But n equals 1 to infinity of minus 1 to the n plus 1 over n. What is this, though? What's it actually? Is that convergent? It satisfies the necessary condition. But why? What's a sufficient condition to observe that that does in fact converge? What it converges to, I happen to know, the natural log of 2. This is the so-called alternating harmonic series, right? The alternating series test says what? I usually abbreviate alternating series test, right? It says if you have, the sum n equals 1 to infinity of, minus 1 to the n plus 1 times like b sub n, where your b sub n's are positive and decreasing with b sub n goes to 0, then the given series converges. Right? This was the alternating series test. That's a sufficient condition for convergence. In some sense, what it really says is that in the context of an alternating series, the nth term test is almost enough just to guarantee convergence, right? So this is a sufficient condition for convergence of a series, but it's not necessary. Why is it not a necessary condition for the convergence of a series? Can you give me an example of a series which converges and yet is not alternating? That would show that it's not a necessary condition. So a guy goes into an ice cream shop. He orders an ice cream, right? And then his friend comes in. He says, I'll pay for a half of an ice cream for him. And then his friend then comes in. And he says to the friend that comes in after him, I'll pay for a half of my ice cream for him. So he gets a quarter of an ice cream. And then the guy after that comes in and he says, well, and then the guy before him says, I'll buy half of his ice cream portion of mine. So he gets where was I? An eighth of an ice cream, right? So then how many ice creams should the ice cream, what do you call the ice cream stooge? The person who scoops the ice cream, what's their name? Do they have the ice cream attendant? What's the proper word here?
Ice cream artist.
The ice cream artist. I like that. So how many bowls of ice cream should the ice cream artist scoop, supposing that they all share bowls?
Natural log of 2 ice creams.
Good guess, but no. The number's on the board, but not in that context. So we're asking the question 1 plus a half, plus a fourth, plus an eighth, and so forth and so on forever and ever. This is a very large ice cream shop. It permits infinitely many customers. Well, this is a what? This is a, we proved this last time, geometric series, right? With a equals to 1 and r is equal to a half, which means it's convergent. So the answer is 2. This story is usually told with beers at a pub, but this is Liberty, so I changed it to ice cream. So, although I have heard some things about the dorms. Okay, anyway. So that the geometric series is not alternating in this context, right? Yet that converges. So that shows you that, the alternating series test is a sufficient but not a necessary condition. In the same way, the geometric series test is a sufficient condition for convergence but not a necessary one. What is a necessary and sufficient condition for convergence of a series? That's the definition of the series, that the limit of the sequence of partial sums exists. That would be a necessary and sufficient condition. So every good definition in mathematics is an example of a necessary and sufficient condition. All right? It's not too much, it's not too little, it's just right. Right? All right, well, that's I think that's an important conversation for us to have because, another good example of sufficient but not necessary is like differentiability of a function, right? If a function's differentiable, we learned in Calculus 1, if a function's differentiable at a point, it's necessarily continuous at the point, right? That's a sufficient condition for continuity at a point is differentiability at the point, right? However, it's not necessary because if you remember, we have the absolute value function at 0, right? That's continuous at 0, but it's not differentiable at 0 because there's a kink in the graph, right? So that's another example I have in the notes for you. But that's all I have to say for this part. I think we should go on and talk about sets now. So we'll do that. So I'm gonna my editorial process in here is very limited, but it occurs to me that it would be helpful for you guys and for me probably in the future to make a hard break right here. So did I get over? Yeah, okay.